This is the EdExcel A-Level Further Maths Paper 3, covering the Further Pure 1 FP1 module, and it's from the 2021 series. Question number 1. The ellipse E has equation x squared over 36 plus y squared over 20 equals 1. For part A, we have to find the coordinates of the foci of E. If we go to the formula book in the A-Level Further Maths section, you will find we have information about various conics. Now, we have an ellipse. We are after, in part A, information about the foci. The foci have coordinates plus minus AE 0. Now, for us to find out what the coordinates of the foci are, we need the value of A, which we can find from the standard form of an ellipse. We also need the value of E, which we can find using the formula b squared equals a squared, lots of 1 minus e squared. So, for part A of the question, we have x squared divided by 36 plus y squared divided by 20 equals 1. You can see here then, A is equal to the square root of 36, which is 6, and B is equal to the square root of 20, which we will leave as square root 20. And so, if we were to use the formula b squared equals a squared, lots of 1 minus e squared, then we have b squared, which is 20, and this is equal to a squared, which is 36, lots of 1 minus e squared. And if we attempt to solve for e, we have 20 divided by 36, which is 5/9, and if we do 1 minus this, e squared is 4/9, and so therefore the value of e is equal to 2 over 3. Now, the foci are given by plus minus AE 0. So, using the fact that the foci are at plus minus AE 0, the coordinates of the foci, we would have plus minus A, which is 6, times by E, which is 2/3, and then 0. And so therefore, the coordinates of the foci will be given by plus minus 4, 0. Now, for part B, we have to find the equation of the directrices of E. Well, for part B, the equation of the directrices is given by the result shown here, x equals plus minus a over e. So, if we use the fact that the directrices are at x equals plus minus a over e, then we have x equals a, which is 6, divided by e, which is 2/3, and so therefore the equation of the directrices, we have x equals plus minus 6 divided by 2/3, which is 9. The equation of the directrices are x equals plus minus 9. Question number 2. For the first part, we have to use the substitution t equals tan of x upon 2 to prove the identity sin x minus cos x plus 1 divided by sin x plus cos x minus 1 being equivalent to sec x plus tan x, where x doesn't equal n pi over 2, where n is an integer. Now, to do this question, we begin with the idea that if t equals tan of x upon 2, then sin x is equal to 2t divided by 1 plus t squared cos x is equal to 1 minus t squared over 1 plus t squared, and tan x is equal to 2t divided by 1 minus t squared. Now, the idea is to start with the left hand side and get to the right hand side. Alternatively, we can start with the right hand side and get to the left hand side. Now, just as some guidance, we can work backwards from the right hand side, which will give us clues as to how to approach the proof. So, if we think of the right hand side, then on the right hand side we have sec x plus tan x. Now again, the purpose of this is to form some sort of clues as to how to approach the question. Now sec is the same as 1 over cos. So we've got 1 over cos x plus tan x, and 1 over cos x, that will be 1 over the result shown here. The reciprocal of this is 1 plus t squared over 1 minus t squared, and then we add on tan x, which is the same as 2t over 1 minus t squared. And because we have a common denominator of 1 minus t squared, this is the same as t squared plus 2t plus 1 divided by 1 minus t squared. T squared plus 2t plus 1, that's the same as t plus 1 all squared. And along the bottom we've got 1 minus t lots of 1 plus t, which simplifies to t plus 1 over 1 minus t. Now, the idea here will be to somehow get to this stage, and from this stage we can work backwards. So, if we begin with the left-hand side, we begin with sin x minus cos x plus 1 divided by sin x plus cos x minus 1. And if we use the t formula, sin x, we know that's the same as 2t over 1 plus t squared. And then we subtract cos x, so we subtract 1 minus t squared over 1 plus t squared. We then add on 1, and then we divide this result by sin x, which is 2t over 1 plus t squared, plus cos x, so we add on 1 minus t squared over 1 plus t squared minus 1. And if I multiply through by 1 plus t squared, we end up with 2t minus 1 minus t squared plus 1 lots of 1 plus t squared divided by 2t plus 1 plus t squared minus 1 plus t squared. And if we expand along the top, we've got 2t minus 1 plus t squared plus 1 plus t squared divided by 2t plus 1 plus t squared minus 1 minus t squared. Simplifying the top, we have 2t squared plus 2t divided by 2t minus 2t squared. And if I divide through by 2, we end up with t squared plus t on the top, and on the bottom t minus t squared. If I factorise out a t from the top and bottom, we've got t lots of t plus 1 divided by t lots of 1 minus t. The t's cancel, so we are left with t plus 1 over 1 minus t. Now we want to somehow get from here to the final step of sec x plus tan x. And we are at this stage, so all we need to do is work backwards. Now this line is equivalent to this line, so t plus 1 over 1 minus t is equivalent to t plus 1 squared over 1 minus t lots of 1 plus t. And if I expand along the top, we have t squared plus 2t plus 1 divided by 1 minus t squared. And if we split this up, this is the same as 1 plus t squared over 1 minus t squared plus 2t over 1 minus t squared. We've got 1 over cos x plus tan x, which is the same as sec x plus tan x. And so therefore we can conclude, as the left hand side is equivalent to the right hand side, we've shown the result. Now for the next part, we have to use the substitution t equals tan of theta upon 2 to determine the exact value of the integral of 5 over 4 plus 2 cos theta d theta in between 0 and pi over 2, giving an answer in simplest form. So, for the next part, we've got t equals tan of theta upon 2. And with this, let's see what our lower limit will equal when theta equals 0. T equals tan of 0 over 2, which is 0, and when theta equals pi over 2, t equals tan of pi over 2 over 2. We've got the tan of pi over 4, which is just 1. And we also know that d theta is equal to 2 over 1 plus t squared dt. And so what we can say then is the integral from 0 to pi over 2 of 5 over 4 plus 2 cos theta d theta becomes well, we've got the integral of 5 divided by 4 plus 2 cos theta. Now cos theta, that's the same as 1 minus t squared over 1 plus t squared. So we will be integrating this, and then we transform the d theta to 2 over 1 plus t squared dt. And then we are integrating in between 0 and 1. So now we need to simplify all of this. Well, if we multiply through by 1 plus t squared, then what we'd end up with is the integral from 0 to 1 of 10, because 5 times 2 is 10, over 4 lots of 1 plus t squared plus 2 lots of 1 minus t squared. dt. And if we expand along the bottom, 4 times by 1 is 4, 4 times t squared is 4t squared, then we add on 2, and then we subtract 2t squared, and then on the top we've got the 10. And now, simplifying this even further, we've got the integral from 0 to 1 of 5 over 3 plus t squared dt. Now, for us to integrate something like this, if we go to the formula book, we will have to use this standard integral as we see over here. So, the integral of 1 over a squared plus x squared is 1 over a arctan of x upon a, where a over here is equal to the square root of 3. So working this out, we've got 5 times by 1 over square root of 3 times by the arctan of t over square root 3. And we are evaluating this between 0 and 1. So, we have 5 times by 1 over root 3, which is 5 over root 3, and in fact we'll take that on the outside. And then here we've got the arctangent of t over square root 3, and if I substitute in my limits, I've got 1 for my upper limit, and then for my lower limit would just end up with 0. So if I attempt to simplify this even further, we've got over here the arctan of 1 over root 3, which is pi over 6, and then I times this by 5 over root 3. So what we'll end up with is 5 over root 3 multiplied by pi over 6, which is 5 pi over 18 multiplied by root 3. So this is the value of the original integral. So the integral of 5 over 4 plus 2 cos theta d theta in between 0 and pi over 2 is 5 pi root 3 over 18 in exact form. Question number 3. Figure 1 shows a sketch of the curve with equation y equals f of x, where f of x is equal to x over the mod of x minus 2. We have to use algebra to determine the values of x for which 2x minus 5 is greater than x over the mod of x minus 2. Now, before we do anything else, here is roughly a sketch of the line y equals 2x minus 5. What we need to do is find out critical values. From there, we can find out the range of values of x which we require. Now, to find the critical values, we need to replace the inequality sign with an equal sign. So, if we do that, we have 2x minus 5 equals x over the mod of x minus 2. So, we've got 2x minus 5 equals x over plus minus x minus 2. Let's begin with the positive. We've got 2x minus 5 equals x over positive x minus 2. And if we were to deal with the negative, we have 2x minus 5 equals x over minus x minus 2. So let's simplify the equation here and attempt to solve. We have 2x minus 5 lots of x minus 2 equals x. So we've got 2x squared minus 9x plus 10 equals x. 2x squared minus 10x plus 10 equals 0. And from this, if we solve, we end up with 5 plus minus square root 5 over 2. And if we attempt to solve this, taking out the minus as a factor here, we have 2x minus 5 lots of x plus 2 equals minus x. 2x squared minus x plus 10 is equal to minus x. Rather, this is minus 10. 2x squared is equal to 10. So x is equal to plus minus the square root of 5. We have our critical values here. Now where would they correspond to? Where the graph crosses the axis over here is at the point 2.5. So now we need to find out the other values. So what will the value here be? Well, that value, if I consider the 5 plus square root 5 over 2, that's equal to 3.61, etc., just above the 2.5. So the value here would correspond to 5 plus root 5 over 2. What would this value correspond to? Well, if I have 5 minus square root 5 over 2, that's the same as 1.38, etc., just less than the 2.5. So here we have 5 plus root 5 over 2. And what's this value going to equal? Well, that value will equal negative square root 5. So we are looking at the x coordinates of the points of intersection. So now what can we do? Well, we are looking for where the red line is greater than the original curve. Now, you can see the red line is greater than the curve in between here and here. Now here we've got an asymptote. So when we come to state the solutions, we have x belonging to a set of real numbers. X will be in between minus 5 square rooted and minus 2. So that's one region. So we've got minus root 5 being less than x being less than minus 2. Or we've got the region in between here and the asymptote. So the next region we've got is 5 minus square root 5 over 2 being less than x being less than 2, or we've got the region beyond this point. So we have x is greater than 5 plus square root 5 over 2. So here is our solution to the inequality. Question number 4. A small aircraft is landing in a field. In a model for the landing, the aircraft travels in different straight lines before and after it lands, as we see in figure 2. The vector VA is in the direction of travel of the aircraft as it approaches the field. The vector VL is in the direction of travel of the aircraft after it lands. With respect to a fixed origin, the field is modelled as the plane with equation x minus 2y plus 25z equals 0, and the vector VA is equal to 3 minus 2 minus 1. For part A, we have to write down a vector n that is a normal vector to the field. So, for part A, we've got the plane, pi1 we'll call it. We've got x minus 2y plus 25z equals 0. And the coefficients of the variables x, y and z will be the coefficients of I, j and k for our normal vector. So our normal vector n, that's equal to I minus 2j plus 25k. So this is our normal vector. Now, for part B, we have to show that n cross VA is equal to lambda lots of 13, 19, 1, where lambda is a constant to be determined. So, if we were to work out for part B, n cross VA, we've got n, which as a column vector is 1, minus 2, 25, and then we cross this with VA, which is 3, minus 2, minus 1. So if we work this out, we can use our calculator. We go to the vector submenu, define the first vector to be 1, minus 2, 25. And then we define our next vector, 3, minus 2, minus 1. And then we cross those. So we end up with 52, 76, 4. And if we take out a 4 as a common factor, then we end up with 4 lots of the vector 13, 19, 1. And so we can see here, lambda is equal to 4. Now, for part C, when the aircraft lands, it remains in contact with the field and travels in the direction of VL. That's what we see in the diagram. The vector VL is in the same plane as both VA and N, as we see in figure 2. So this shaded region is a plane. We have to determine a vector which has the same direction as VL. Well, we are looking for the line VL, and that's the intersection of this plane here with this plane here. So if I call this plane pi1, and if this plane is pi2, we are looking for the vector line where pi1 and pi2 intersect. Now, for us to find out what pi2 is, we need a normal vector, and the normal vector can be obtained by crossing VA and N together, but we've already worked that out. When crossed together, we get 13, 19, 1 as our column vector. And so, for part C, we require the plane pi2, and the normal vector will be given by 13i plus 19j plus k. So therefore, for us to find out what the equation of the plane is, we have r dot width 13, 19, 1, and this is equal to some position vector on the plane, which is VA, and we already know what that is. That's 3 minus 2 minus 1. And then this will be dotted with our normal vector 13, 19, 1. So if we work this out, we've got r dot with 13, 19, 1, and this is equal to, well, here we've got 3 times by 13 plus minus 2 times 19 plus minus 1 times 1, which is 0. And if we were to write down the Cartesian equation, we can therefore conclude pi 2, that's given by 13x plus 19y plus z equals 0. Now, if I call this equation 1, and if I call this equation 2, we need to solve equation 1 and 2 simultaneously. Now, we've got 3 variables but only 2 equations, so we can let one of the variables equal some constant. For example, we could let z equal 1. And if we do that from equation 1, we have x minus 2y plus 25z, so we've got 25 lots of 1 equals 0. And therefore, x minus 2y is equal to minus 25. We'll call this 3. And with pi 2, we've got 13x plus 19y plus 1z equals 0. So therefore we've got 13x plus 19y equals minus 1. We'll call this equation 4. We can now solve equation 3 and 4 simultaneously, and if we were to do that, let's go to our simultaneous equation solver. We've got 1x minus 2y minus 25. We've also got 13, 19 and minus 1. So we end up with a value of x of minus 53 over 5, a value of y 36 over 5, and the corresponding z is equal to 1. And so therefore, we can conclude VL is in the direction of minus 53 over 5i plus 36 over 5j plus k. And now for part D of the question, we have to state a limitation of the model. Well, the paths may not be linear. That is the paths of VA and VL. So a potential limitation is that the paths may not be linear. Question number 5. The parabola C has equation y squared equals 32x, and the hyperbola H has equation x squared over 36 minus y squared over 9 equals 1. Let's just call this equation 1, and let's call this equation 2. Now, for part A, we have to write down the equations of the asymptotes of H. Now, in the formula book, for hyperbolas, the asymptotes will be given by x over A equals plus minus y over b. And you can see from h, a is equal to 6, b is equal to 3. So for part A then, for the asymptotes of h, we have x over a equals plus minus y over b, and knowing that a is 6 and b is equal to 3, we have x over 6 equals plus minus y over 3, from which we can conclude the asymptotes have equation y equals plus minus 1/2 x. Now, for part B, the line L1 is normal to C and parallel to the asymptote of h with positive gradient. The line L2 is normal to C and parallel to the asymptote of h with negative gradient. We have to determine an equation for the line L1 and the line L2. So for part B, if we take a look at the parabola, we've got y squared equals 36x, and if I differentiate implicitly, we've got 2y dy over dx equals 36, and therefore dy over dx equals 36 over 2y, which is 16 over y. This 16 over y would represent the gradient of the tangent, and so therefore the gradient of the normal is the negative reciprocal of 16 over y, which is minus y over 16. Now, what we can do is find out the gradient of L1 and L2. So if I take a look at what we know about L1, we know L1 is parallel to the asymptote of h with positive gradient. So therefore, if the gradient of L1 is a half the positive asymptote, then we have minus y over 16 equals 1/2. And from this we can see y is equal to minus 8. And similarly, if the gradient of L2 is minus 1/2, then we would have minus y over 16 equals minus 1/2, in which case you can see y is equal to positive 8. And with this we can find out the corresponding x values by substituting back into the parabola. We've got y squared equals 36x. So we've got y squared. So here y is both equal to minus 8 and 8. So squaring those will give the same value. So minus 8 squared equals 8 squared equals 36x, rather 32x. So we've got 64 equals 32x. X equals 2. And if x equals 2 and y is equal to plus minus 8, for the line L1, we've got y minus minus 8, so that will be the same as y plus 8. That's equal to its gradient, which is positive 1/2, lots of x minus 2. In other words, y equals 1/2 x minus 9. And we also have L2, which has equation y minus 8 equals minus 1/2 lots of x minus 2, in which case we can conclude y is equal to minus 1/2 x plus 9. So if I call this equation 3, and if I call this equation 4, you can see then we found the equation of L1 and L2 respectively. Now for part C, the lines L1 and L2 meet H at the points P and Q respectively. We have to find the area of the triangle OPQ, where O is the origin. So here is a diagram of everything we know so far. We've got the parabola, we've got the asymptote shown in blue, and we've got the equations of the normals shown in red. Now, we know that these lines intersect the parabola, so we can find out the coordinates of P and Q, where here we've got the point P, here we've got the point Q, and here we've got the origin. So we need to find out what P and Q are. We can do this by substituting 3 and 4 into equation 2. The steps will be identical. So let's split our page down the middle. So on this side we will substitute in 3 into 2, and on this side we will substitute in 4 into 2. So we've got x squared over 36 minus y squared. Now we know what y is. That's 1/2 x minus 9. So we subtract 1/2 x minus 9 squared over 9. This is equal to 1. So we have x squared over 36 minus 1/4 x minus 9x plus 81 divided by 9 equals 1. Multiplying through by 36, we've got x squared minus, well here we've got 36 times by a ninth, which is 4, and multiplying that by the top line here, we've got minus x squared plus 36x, because the minus and the minus give a plus, and then we've got 4 times by 81, which is 324. Don't forget the minus. This is all equal to 36. So 36x is equal to 360. So x is equal to 10. And if x is equal to 10, that means the corresponding y value is 1/2 lots of 10 minus 9, which is minus 4. And similarly, 4 into 2, we've got x squared over 36 minus 1/2 x plus 9 divided by 9 equals 1. So x squared over 36 minus 1/4 x squared minus 9x plus 81 divided by 9 equals 1. Multiplying through by 36, we end up with x squared minus x squared plus 36x minus 324. This is equal to 36. 36x is equal to 360. X is 10. And therefore the corresponding y coordinate, we've got minus 1/2 lots of 10 plus 9, which is equal to 4. L1 and L2 intersect H at 10 minus 4 and 10, 4 respectively. So if I go back, we have L1 here, L2 here. So the coordinates over here are 10, 4, and here we've got 10 minus 4. Now we need to find out the area of this triangle shown shaded in blue. So what we need to do is find the area of the triangle OPQ, and so therefore that area, we've got 1/2 times by, well, here the height is 4 take away minus 4, which is 8. The length here is 10. So we've got 1/2 times by 10 times by 8, which is 40 units squared. So this is the required area. Question number 6, we've got the Taylor series expansion of f of x about x equals a shown here, and we're given that y equals 1 plus natural log x all squared, where x is greater than 0, and for part A we have to show that d squared y over dx squared is equal to minus 2 times the natural log of x over x squared. We begin with y equals 1 plus natural log of x squared, and if we differentiate using the chain rule, we have 2 lots of 1 plus natural log x to the power of 1 multiplied by 1 over x. So we divide this by x. And if we expand the brackets, we have 2 plus 2 times by the natural log of x over x. And if we differentiate once again, d squared y over dx squared using the quotient rule, where u is 2 plus 2 natural log x and v is x, we've got v times by u dash, which is 2 over x, minus u, which is 2 plus 2 times by the natural log of x, times by v dash, which is 1, and then we divide this by v squared, so we divide by x squared. We've got 2 times by x over x, so that's the same as 2, and then we subtract 2, and then we subtract 2 times by the natural log of x, and then we divide by x squared. So we end up with minus 2 times by the natural log of x over x squared. It's the result we wanted to show. And now we have to find the third derivative. So again, we need to use the quotient rule. So u is equal to minus 2 times the natural log of x. V is equal to x squared. So we've got v times by u dash, which is minus 2 over x, minus u, which is minus 2 times the natural log of x, times by v dash, which is 2x, and then we divide by v squared, so we divide by x squared squared. So if I simplify, we've got x squared times by minus 2 over x, so that's minus 2x. And then the minus and the minus give a plus. We've got 2 times by 2x, which is 4x. We times that by the natural log of x. And then we divide by x squared squared, which is x to the 4. And tidying this up even further, we end up with minus 2 plus 4 times the natural log of x over x cubed. That's the result we wanted to work out. And now for part C, we have to determine the Taylor series expansion about x equals 1 of 1 plus natural log x all squared in ascending powers of x minus 1 up to and including the term in x minus 1 all cubed. We have to give each coefficient in simplest form. Well, using the result here, we need to work out f of 1, f dash of 1, f double dash of 1, and then f triple dash of 1. And then we can use our formula. So for part C, y of 1 will equal 1 plus natural log of 1 squared. 1 squared is 1. Y double dash of 1, rather y dash of 1, that's equal to 2 plus 2 times the natural log of 1 over 1, which is 2. Y double dash of 1, that's equal to minus 2 times by the natural log of 1 over 1 squared, which is 0, and y triple dash of 1 is equal to minus 2 plus 4 times the natural log of 1 over 1 cubed, which is minus 2. So we've worked out all the different derivatives. Now, if we substitute back into the Taylor series expansion, we can see then y is equal to 1, which is y of 1, plus 2 over 1 factorial times x minus 1, and then we've got 0 over 2 factorial times x minus 1 squared, and then we've got minus 2 over 3 factorial times x minus 1 cubed, and then we've got higher order terms. And so therefore, 1 plus the natural log of x squared is equal to 1 plus 2 lots of x minus 1 minus 1/3 lots of x minus 1 cubed plus higher order terms. Now for part D, we have to use this series to evaluate the limit as x tends towards 1 of 2x minus 1 minus minus 1 plus natural log x all squared over x minus 1 cubed, explaining your reasoning clearly. So, for part D, we've got the limit as x tends towards 1 of 2x minus 1 minus 1 plus natural log of x squared over x minus 1 cubed. And because when evaluated this is something of the form 0 over 0 and indeterminate form, what we can do is instead use our series expansion. So we've got the limit as x tends towards 1 of 2x minus 1 minus, and then we subtract this result here. So perhaps if we write this on a new line, so we subtract this result here, and then on the bottom we divide by x minus 1 cubed. So we've got the limit as x tends towards 1 of 2x minus 1, and then here we've got a minus another 1, and then if I expand this bracket, we've got minus 2x plus 2, and the reason we've got plus 2 is because we've got 2 times by minus 1 times by another 1, so that's going to be 2, and then minus and a minus give a plus. So we add on 1/3 lots of x minus 1 all cubed plus higher order terms. And on the bottom, we divide by x minus 1 cubed. So we've got the limit as x tends towards 1. And here 2x minus 2x is 0, minus 1, minus under 1 plus 2 is 0. So we've got 1/3 lots of x minus 1 all cubed plus higher order terms divided by x minus 1 all cubed. So we've got the limit of x tends towards 1, and here we have 1/3 plus higher order terms. And the reason we need to include the higher order terms is because we're still taking the limit. So here we've got terms of the form x minus 1 to the power of k, which we didn't include. So here this limit will end up equaling 1/3, because if I substitute 1 into here, the rest of the terms will disappear. So what we can put for a conclusion, we have as the remaining terms will become 0 in the limit as they are multiples of x minus 1 to the power of k. Remember, when I take the limit of x minus 1 to the power of k as x tends towards 1, higher order terms will essentially disappear, which is why they tend to 0. So the remaining terms are 0, we are left with then 1/3. Question number 7. With respect to a fixed origin O, the line L has equation r minus the vector 12i plus 16j minus 8k times 9i plus 6j plus 2k equals the 0 vector. The point A lies on L such that the direction cosines of OA with respect to the I, J and K axis are 3/7, beta and gamma. We have to determine the coordinates of the point A. First of all, let's rewrite the line L as a column equation. And if we rearrange from here, you can see R is equal to the vector 12, 16, minus 8 plus lambda lots of 9, 6, 2. Now, we can find the position vector of A using the equation here, and that's given by OA equals 12 plus 9 lambda, 16 plus 6 lambda, minus 8 plus 2 lambda. And from this information, we can find the direction cosine of L in the x direction. And that's shown by the result here. We've got 12 plus 9 lambda equals 12 plus 9 lambda over the square root of 12 plus 9 lambda squared plus 16 plus 6 lambda squared plus 8 plus minus 8 plus 2 lambda squared equals 3/7. And we were given that information here. This is just with respect to the I-axis, in other words, the x direction. And if we square both sides, we end up with 12 plus 9 lambda all squared over 12 plus 9 lambda squared plus 16 plus 6 lambda squared plus minus 8 plus 2 lambda squared equaling 9/49. And now at this point we need to tidy all this up and solve. So expanding 12 plus 9 lambda all squared, we get 144 plus 216 lambda plus 81 lambda squared. And we divide this by 144 plus 216 lambda plus 81 lambda squared, which is this bracket simplified, and this bracket simplified, we end up with 256 plus 192 lambda plus 36 lambda squared, and this bracket simplified, we end up with 64 minus 32 lambda plus 4 lambda squared, and this is of course equal to 9/49. And if we simplify, the top remains as it is, and collecting like terms on the bottom, we end up with 464 plus 376 lambda plus 121 lambda squared, and this is equal to 9/49. And now we need to solve this equation. So if I cross multiply, I've got 49 lots of the result here, which is equal to 9 lots of the result shown here. And if I expand the left hand side, we get 7056 plus 10584 lambda plus 3969 lambda squared. And on the right hand side, we end up with 1089 lambda squared plus 3384 lambda plus 4176. And taking everything over to one side, we end up with 2880 lambda squared plus 7200 lambda plus 2880 equals 0. And therefore, we end up with 2 lambda squared plus 5 lambda plus 2 equals 0. And if we factorize, we've got 2 lambda plus 1 lots of lambda plus 2 equals 0, from which you can see lambda is either equal to -1/2 or -2. Now, with each of these values of lambda, let's find the position vector of A, and then with that we also need to verify that the direction cosines will equal 3/7. So let's take a look at the value of lambda equals -1/2. If we were to find out what OA is, OA, that's equal to 12 plus 9 lots of -1/2, 16 plus 6 lots of -1/2, and we've got -8 plus 2 lots of -1/2, which is 15/2, 13, and -9. And with this, let's find out what the direction cosine is. we have 15 over 2 divided by 15 over 2 squared plus 13 squared plus minus 9 squared, and then this is square rooted. So if I work out what this is, we've got 7.5 over 7.5 squared plus 13 squared plus 9 squared square rooted, which is 3/7. And now let's do the same thing with the value of lambda equaling minus 2. So from here, the vector OA then will equal 12 plus 9 lots of minus 2, 16 plus 6 lots of minus 2, minus 8 plus 2 lots of minus 2, which if we simplify, we get minus 6, 4, minus 12. And now if we find the direction cosine, we've got minus 6 divided by minus 6 squared plus 4 squared plus minus 12 squared, and then this is square rooted. And if I work out what this is, I've got minus 6 plus, rather minus 6 over square root of 6 squared plus 4 squared plus 12 squared. So here I get minus 3/7. So we need to reject the value of lambda equaling minus 2. And rejecting the value of minus 2 will leave us with the following. We've got A with coordinates 15 over 2, 13, and minus 9. This is the only solution. Question number 8. A community is concerned about the rising level of pollutant in its local pond and applies a chemical treatment to stop the increase of pollutant. The concentration X parts per million ppm of the pollutant in the pond water T days after the chemical treatment was applied is modelled by the differential equation shown here, dx over dt equals 3 plus cos t over 3x squared cos t minus a third x than t. When the chemical treatment was applied, the concentration of the pollutant was 3 ppm. We have to use the iterative formula shown here once to estimate the concentration of the pollutant in the pond water 6 hours after the chemical treatment was applied. Now, if we are considering 6 hours, well, if x is in days, 6 hours is 0.25 days. Now, what we can see from here then is if t is 0.25 days, that means the value of h will equal 0.25. We've got one iteration after 6 hours, so that will correspond to a step of 0.25. So, if we were to use our iterative formula, well, we know already T0 equals 0, and we also know X0 is equal to 3. We've got 3 ppm. And with this we can find out what dx over dt naught is. So we've got 3 plus cosh of 0 over 3 lots of 3 squared lots of cosh of 0. Remember, cosh of 0 is just 1, minus 3 lots of tan of 0 over 3. And it turns out we get 4 over 27. And now if we use the iterative formula, we can see then we've got dx over dt naught being approximately equal to x1 minus x naught over h. So we've got 4 over 27 being approximately equal to x1 minus 3, which is what x naught is, divided by h, which is 0.25. And if we were to find out what x1 is, x1 then is approximately equal to 4 over 27 times 0.25 plus 3, which is 82 over 27 ppm. Now for part B, we have to show that the transformation u equals x cubed transforms the differential equation shown here into this differential equation here, du over dt plus u tan t equals 1 plus 3 over cosh t. So for part B, we begin with u equals x cubed. And if we were to differentiate with respect to t, du over dt, this will equal, using the chain rule, dx over dt times du over dx. So we've got 3x squared dx over dt. So all I've done over here is differentiated u with respect to x to get 3x squared and then multiplied by dx over dt. Now, if we go back to the question, we already know what dx over dt is. That's the result shown here. So, knowing that, what we can now do is replace the dx over dt with 3 plus cosh t over 3x squared cosh t minus x tan t over 3. So what we have done over here is replace the dx over dt with equation I. And if I expand out, well, 3x squared over 3x squared, that will cancel out. So we are left with 3 plus cosh t over cosh t minus, well, here we've got 3x squared times by minus x, so that's going to be minus 3x cubed, dividing that by 3, we'd just have minus x cubed than t. And we know that x cubed is equal to u. So we've got 3 plus cos t divided by cos t minus u than t. And therefore we've got 3 over cos t plus cos t over cos t minus u times by than t. So we've got 3 over cos t plus 1 minus u times by than t. And this is what du over dt is equal to. So therefore, if we rearrange to write the result in the required form, you can see then du over dt plus u than t is equal to 1 plus 3 over cos t. And now we have to find a general solution to this differential equation. Now, for us to find a general solution, we can use the integrating factor method. So for the integrating factor method, the integrating factor is equal to e to the power of than t dt. So we've got e to the power of the natural log of the mod of than t, rather times by the natural log of e to the natural log of the mod of cos t, which is just equal to cos t. And therefore we've got u multiplied by cos t equals the integral of cos t multiplied by 1 plus 3 over cos t dt. And tidying this up, we've got u cos t equals the integral of cos t plus 3 dt, because cos t times 3 over cos t is just 3. So I've got u cos t equals, well, if I integrate cos, I get sine. And if I integrate 3, I end up with 3t, and then I add on a constant c. And if I divide through by cos t, we've got u equals sine t over cos t plus 3t over cos t plus c over cos t. And therefore this is our general solution. And knowing that u is equal to x cubed, we've got x cubed, which is equal to all of this. So x cubed is equal to sine t over cos t plus 3t over cosh t plus c over cosh t. And actually, if we're feeling really technical, we could see that sin t over cosh t is equal to sin t, and then the rest will stay the same. So this is our general solution to the differential equation. And now we have to find an equation for the concentration of pollutant in the pond water T days after the chemical treatment was applied. Well, here, for part D, all we are doing is thinking about what happens when t equals 0. And when t equals 0, x is equal to 3. So I've got 3 cubed equals tan of 0 plus 3 lots of 0 over cosh of 0 plus c over cosh of 0. So 3 cubed is 27. So I've got 27 equals 0 plus 0 plus c over 1. And therefore, we can conclude c is equal to 27. And knowing that c is equal to 27, we can therefore conclude x cubed is equal to tan t plus 3t plus 27 over cosh t, bearing in mind we've combined the denominators here. And if I cube root, we end up with tan t plus 3t plus 27 over cosh t to the power of 1/3. So that's how we approach part D. And now for part E, we have to find the percentage error of the estimate found in part A compared to the value predicted by the model, stating if it's an overestimate or an underestimate. So with t equaling 0.25, which is 6 hours, so t equaling 0.25, x is equal to tan of 0.25 plus 3 lots of 0.25 plus 27 divided by cosh of 0.25. And this is raised to the power of 1/3. So if I find out what x is at t equals 0.25, we've got hyperbolic tan of 0.25 plus 3 lots of 0.25 plus 27 over hyperbolic cosine of 0.25, and then we raise this to the power of 1/3, So we get x equals 3.005. And therefore, for the percentage error, we've got 3.005 minus 82/27 divided by 3.005, etc., times 100. So we've got this minus 82/27 over this times 100. Done that the wrong way around, but I'll just straighten this up. So here we had 82/27 minus 3.005 over that. So we get 1.05% to 3 significant figures. And crucially, we've got an over estimate.